Continue. Perfect. And that's our lecture. It's hard to believe, lecture 21 in high dimensional probability and applications to data science. Okay, so we finished our big stretch on applications, 5 lectures on applications. We're falling back on foundations. We'll do maybe 3 or 4 lectures in mathematical foundations, and then we'll again do the applications. And to move forward, it would be good to have some uniform background in linear algebra. And I know you guys have that already, but I will, I decided to just spend this class, just one class, on on refresher on linear algebra, because there are some topics that go uncovered, and some topics are not, you know, in the traditional linear algebra course, they're not very emphasized, and this is actually very important in data science. And so that's what we'll do now. A refresher in linear algebra. If you need more, if at some point what I'm saying doesn't sound familiar or you want more, in the lecture notes that I post, you will find that. They are more detailed than what I'm telling now. So not the video recording, but check the actual lecture notes that are posted on the website. There are proofs, and there are more like in-depth discussion there. Good. Okay. So problem number 1. So the theorem number 1 in linear algebra that's extremely important is the spectral theorem, the spectral decomposition. We will use it a lot from now on. And the spectral theorem for symmetric matrices is one of the cornerstones of linear algebra for any symmetric n by n matrix A. Here's what we know about eigenvalues, and here's what we know about eigenvectors. All right, what do we know about eigenvalues? You tell me.
They're non-negative.
Not necessarily, because if you take the matrix A and take the minus A, it's still symmetric, right? You take symmetric matrix, you take minus A, it's still symmetric, but all eigenvalues will be automatically like flip the signs. So they're not necessarily. Yeah, go ahead.
They're real.
Real. Exactly, they're real. That's the point. And they're non-negative if the matrix is positive semi-definite. So you're right there. But if you just assume symmetry, they're real. Generally, as we know, any matrix has eigenvalues, n of them, right? And this is just because they are the roots of the characteristic polynomial. And the fundamental theorem of linear algebra tells us that, you know, polynomial and degree n must have n roots. Complex, though. So they may be complex. But if the matrix is symmetric, then the eigenvalues are real. So all eigenvalues, are real. And I will arrange them just to choose some order here like this. Starting from the largest, we'll always assume that lambda 1 will be the largest, and then they're arranged like this. Real. And the eigenvectors, what do we know about them?
They are orthogonal for different lambdas.
Exactly. They are orthogonal for different lambdas. And even if there is multiplicity, if let's say lambda 1 equals lambda 2, I can still make them orthogonal, right? There is a whole subspace. Maybe if lambda 1 equals lambda 2, the entire plane spent by this, the eigenspace consists of eigenvectors corresponding to this lambda, but I can always choose, even then, I can choose the orthogonal vectors. So I can always choose that, let's say, unit vectors, I can normalize them, the unit eigenvectors, u1 through un, corresponding to these eigenvalues, are orthonormal. And if such, we have n orthonormal vectors in dimension n, and therefore they form the orthonormal basis of Rn. Perfect. Okay. Okay, remember that spectral theorem? Good. Cool. Okay, immediate corollary, almost immediate corollary to this is a very useful representation of a theorem. Representation that helps us kind of visualize the geometric properties. And that's called the spectral decomposition. Spectral representation or spectral decomposition of a matrix. Any symmetric matrix can be written as some lambda I, which is eigenvalues, ui transpose, where ui's are eigenvectors. The sum goes up to the rank. And yeah, and that's it. Like this. How do you see this? Well, let's prove it. Let's just check any x, take any x, and multiply both sides by x, like a test vector. Okay. If this holds, if the equation holds for any x, then the matrices are the same. So let's do this. I can take x, and what we will do, we will expand x into the basis. uix, ui. So this is the orthonormal, this is a basis expansion. Yep, familiar, right? So ui's are orthonormal vectors. Therefore, it's like the usual orthogonal basis. You can expand every vector with respect to ui's, and this is expansion. Now we multiply both sides by a, and we get ax equals, and then by linearity, I can pull a into here, aui. And just by the definition of the eigenvector, aui equals lambda I ui. That's a definition of the eigenvector. And so this becomes, okay, and I would like to pull out x now. So I will pull out x. How can I do this? I think it's, okay, correct me if I'm wrong, but I think it will be like this. Lambda I ui transpose times x. Because I can think of this as ui transpose x. Yeah. Good. Ui transpose x is the same as the inner product between ui and x. Okay, so that's good. Okay, so what do we have? We have a times x equals what we need times x for any x. If this is a metric, let's call this b. So we have ax equals bx for all x. And that means that the matrices are the same, that a equals b, which is what we claimed. Agreed? Any questions? Everything is familiar? Everything is good?
May I ask a more philosophical question?
Yeah, sure.
Why is this decomposition useful in exactly this this form? Because we, for symmetric matrices, we know that it is diagonizable, and therefore it can be written without ui transpose. You can write similar sum immediately. Well, not with the vectors though. And why? I'm seeing this first time in your lectures. This note.
Okay, I'm glad you're seeing it the first time, because I was worried maybe people work with us all the time. But Maxim, tell me more. So if you well, I don't really understand your question. So you say if the matrix wasn't symmetric, it's
no. I'm saying that why do we care about vectors? So we can just, why don't we work with it in this form? Why don't we write just a equal like diagonal matrix with lambda 1, lambda 2, lambda and so on. Why is this form useful?
Maxim, help me more. Why don't we write what? Give me an alternative. A equals what?
A equals just matrix. Okay.
I can maybe I guess the question why we crashing on the sum where different lambda is in one summand. Why we don't take the diagonal matrix where on diagonal is eigenvalues? If I understand the question right.
And so, in general, we know that any matrix can be written as some matrix T. In Ukrainian, it's called matricя переходу. I don't necessarily remember how it's translated. So T to the power -1 times diagonal matrix with something on diagonal, and then T.
And then T, yes. Exactly. Okay.
So for and I mean, for real matrix, this D will be diagonal, and T actually, as far as I know, can be how is it translated?
Yeah, say it in Ukrainian.
In some form. Orthogonalna matrix. Orthogonal matrix.
Orthogonal.
Yes.
Yeah, that's exactly what I'm trying to say next. Yeah.
Oh.
Yeah, that's
okay.
Yeah.
Okay.
I was trying to say exactly this next thing, so that I can write this in this form where T is an orthogonal matrix, and so that will be and maybe that's more familiar to you. So that would be the matrix form of the same spectral decomposition. Why?
Okay. I'm sorry.
Yeah, that's right. But why is this form? Why is like a sum is as an important thing? Let me think. Like off the top of my head.
I can explain more. So why am I asking this question? So in the hints to our homework previous, you wrote exactly this decomposition for positive semi-definite matrices, but it wasn't like necessary in that case. In this form, second what we are discussing, it's at least for me, it was more familiar, and I mean, vectors were not actually very important there.
Okay. So Maxim,
that's why I'm asking.
I understand. Yeah. Okay. I can explain why exactly this form can be useful. And let's actually, we can actually even do this now. So this form, let's see. So maybe this is what you're more familiar with, and I'm claiming that this form, that the new form, is sometimes actually more enlightening to you. Although of course they're equivalent, but this is more enlightening. How? Here in this form, UI transpose, because UIs are vectors, each block UI transpose is a rank 1 matrix. You agree, right? It's just UI vector times vector. It will be rank 1 matrix. So in this form gives you an explicit representation in terms of rank 1 matrices. Now, suppose like a data scientist, let's say you have a matrix and you would like to simplify it. You would like to make it a lower rank 5, let's say. What is the best possible approximation to a given matrix by a matrix of rank 5? How do you find that matrix of rank 5? The answer from here is kind of immediate. What you need to do is you need to truncate the sum. You need only to take the first 5 terms. Remember, lambda i's are the largest eigenvalues, so they explain the most about this matrix. So you just take the first, like lambda 1 u and lambda 2 u up to 5, and that is the best possible representation of a matrix, of a given matrix A with a matrix of rank 5. So, for example, for this question, I think it's this form is very useful.
Okay, thank you. That's helpful.
That's helpful. Yeah, it would be difficult to guess that approximation from this form. I think, but it's easier on this level. But they're, of course, they're equivalent, and that's exactly what I'm going to say now. So thank you, Maxim, for asking this question. And anybody else, if you want to ask something at any time, please do so, or make an observation. Yes. So in the matrix form, just like Maxim and Alexandra noted, in the matrix form, we can just write this as A, I'll change notation from Maxim's U, lambda, U transpose. This is because, okay, so let's see. So A, let's see, A, this is our matrix A, square matrix A equals U lambda U transpose. Okay, now you tell me what's going to be lambda. Lambda is going to be diagonal. What do we put on the diagonal? That should be obvious, guys. What is it?
Lambda i's.
Exactly, eigenvalue. So lambda I is a storage unit for eigenvalues, obviously, and U will be the storage unit for eigenvectors. And if we interpret this correctly, I think it's like this. The columns should be eigenvectors, Ui, and then U transpose, of course, will be the rows. Transposed will be like that. Right? And if you multiply these matrices, you will see that you'll get exactly this form, that this and this are equivalent to each other. Now, because UIs are orthogonal columns, it means that this matrix U is orthogonal. Is orthogonal matrix, and in our notation, we'll denote it like O of n, orthogonal group in dimension n, and lambda is diagonal. Perfect. So you guys have seen this form before, so that's no big news here. So we'll give three interpretations of this theorem. First, in matrix form, it's that. Second, in geometric form, and third, in optimization form. In geometric form, we can see A as a linear transformation, as an operator, as a function that takes something and outputs something. So it takes a vector x and outputs ax. It's a linear transformation. How does it act? Suppose this is a unit sphere, for example. What does it do to the unit sphere? What's the image of the unit sphere? Ellipsoid, right? So it takes you to some ellipsoid. What ellipsoid? So if this is U1 and this is U2, let's say, what it does, it's obvious that it just stretches these directions. AU1 is lambda 1 U1. So it just stretches or maybe contracts these directions, lambda 1 U1 and lambda 2 U2. And does nothing else. So it's just a stretch UI lambda I times. So that's all symmetric matrices do. So they identify certain directions in space and then they just stretch and contract, and that's all they can do. That's geometric form. In the optimization form, by the way, sorry, and these directions are orthogonal, that's important. In the optimization form, we can think about these directions as the extreme directions in some sense, right? So this U1 corresponding to the largest eigenvalue, this direction will be stretched the most of all the directions in space. So in particular, I can write something like this. Lambda 1 is a U1, the inner product. So imagine what happens. We stretch that direction, we get lambda 1 U1, and then we project it into the same direction, which is the same. So that's lambda 1. But what I'm claiming is that this quadratic form is maximized by U1. So if I take any other X transpose AX, so this is like, yeah. So if I take any other quadratic form among all unit vectors, then the biggest it can be is on the first eigenvector. So U1 is argmax, which means that it's maximized at the first eigenvector, and the value of that quadratic form is lambda 1. Okay, you agreed? So I just expressed the idea that the first eigenvector stretches or contracts the direction the most. And what about lambda 2? How do we express lambda 2? So this direction is the direction of the biggest stretch. Then what do we do? Then we factor out that direction. So we project everything on the orthogonal and identify the direction in the orthogonal space that stretched the most. And that's going to be U2. So maximum x, we still maximize the same quadratic form, but now we're removing the first eigenvector. So x orthogonal to U1 unit vector. We take like a residual here. And U2, the second eigenvector, will maximize that. What do we do next? Well, it's obvious, right? So you remove the first and the second eigenvector, you contract, you project everything on the residual, and still the quadratic form, you still maximize the quadratic form, and you get U3. And so on and so forth. So this is the meaning, the geometric meaning of the eigenvectors and the optimization meaning of eigenvalues and eigenvectors. Okay, good. We'll use it a lot of times. So they are maximum, they maximize this quadratic form, the canonical quadratic form X transpose AX, iteratively, so to speak. Good. Any questions? Any philosophical remarks? Non-philosophical, whatever. Yeah. Good. Good. All right. This is symmetric matrices. This is all the story was about symmetric matrices. Now, for non-symmetric matrices, we need to modify this, and the modification is very easy. There will be different vectors. It will be UI and VI transpose. Or in this form, in the matrix form, there will be different matrices here, like T and S. And that's called singular vector decomposition, singular value decomposition. So for general, let's say M by N matrices. We have singular value decomposition, which is just like the spectral decomposition. Some numbers, UI, VI transpose, different vectors. So that's the biggest change here. R is still the rank, as before. And sigma 1s and sigma 2, we can make them non-negative. They are called singular values, not eigenvalues, but singular values of A. The UIs. They're vectors and they're called, well, now we have UIs and VIs. So UIs are called left singular vectors and VIs right singular vectors, for the obvious reason. And VIs are called right singular. Vectors. Are you generally familiar with this, guys? Yeah, singular value decomposition. Okay, so this general decomposition, we can deduce it from let's give an informal argument, informal proof. We can deduce it from the spectral decomposition. But that one works only for symmetric matrices, so we need to make asymmetric. So we will apply it for A transpose, which is symmetric. Actually, we will apply it twice for A transpose A2. and we'll see what happens. So we'll apply it twice. So A transpose. That's a symmetric matrix. What is this matrix? Now let's write this. You know what, guys? Let's guess what these sigma i's, u i's, v. Suppose we know the singular value decomposition, and let's guess first what the sigma i's and u i's would look like. So if we know that A is like this, then A transpose would be, well, obviously this. I'm just rewriting here. So sum sigma I, u I, v I transpose. Let's say sigma j, vj, ui, uj, vj transpose. Okay, so we multiply the sum term by term, double sum, sigma I, sigma j, ui, vj transpose, or vi transpose. It's a mess, sorry, but it will simplify soon. Oh, I forgot to put the transpose. Did I?
The sum should be transposed, or we should change the order.
Exactly, Vj. So how do you transpose the ui vj transpose? Is Vj ui transpose. The transposition changes the order. Yeah, thank you. So that will work now. Vj ui transpose. Perfect. Okay. So this thing here, that would be the key to simplification, because this is the same as the inner product between Vi and Vj. And remember, they're orthogonal. If they're orthogonal, then they will be 1 if I equals j, 0 if I is not j. So I need to add this orthonormal maybe in the statement. All right. So with that, everything, like all these off-diagonal terms are gone. And we have only the diagonal terms, sigma I squared, ui transpose. Very nice. Yep. All I not j go away, and only I equal j stays. And that's what it is. Perfect. And very similarly, if you do the same exercise for A transpose A, I will get, I guess not surprisingly, vi transpose. Good. So what do we get from this? We get, first of all, that sigma i's, let's see, from this. This is a spectral decomposition for A transpose. So it means that sigma I squared must be the eigenvalues of A transpose. All right, good. So we computed what sigma i's are. Sigma i's are the square roots of the eigenvalues of A transpose. You agreed? That's because we get the spectral decomposition, and that means that sigma I squared must be the eigenvalues of A transpose from the spectral decomposition. Perfect. And similarly, they're the same numbers, so this should be the square roots of eigenvalues of A transpose A. And if A itself was symmetric, then this will be what? This will be just, I guess, absolute value of lambda i's, right? Of A. Because A squared, lambda I squared will be lambda I squared, and yeah. So this, we just demystified the singular values. So the singular values of A are just the eigenvalues of A transpose, or A transpose A, up to the square root. All right. What's the left singular values? Vectors, ui. Just from this, ui's are the eigenvectors of A transpose, and vj's from this are eigenvectors of A transpose A. Good. So that's how we compute this, the singular value decomposition. We take AA transpose, let's say, compute AA transpose, compute its eigenvectors, call them UIs. Then we compute the singular value. Sorry, then we take A transpose A, compute eigenvectors. This will be VJs. And the eigenvalues in either case will be sigma. So that's it. That's our signal value decomposition. Now that we know what they should be, the exercise is to prove the theorem. Now we know how to guess them and then just stick them in the theorem and try to prove them. We'll not do that. Okay, singular value decomposition. Okay, good. Good. Let me copy this. Copy. Maybe here, paste. Where'd it go? Same remarks. So let's reinterpret now the singular value decomposition in three ways: matrix form, geometric form, and the optimization form. Let me show you how we did this for symmetric matrices. In the matrix form, it was this. The geometric form, it was this. We just said that A just stretches some directions. And the optimization form is just optimization some quadratic forms. Let's do the same here. In matrix form, we can write A as previously it was U, then the diagonal matrix, and then U transpose. But now it will be different, not U, but V transpose, for the obvious reason. Here is how it goes. A, that's our matrix A, equals U sigma V transpose. Now the dimensions are different. M N and I believe NN, something like that. U. So okay, sigma is a storage for singular values. So it's on the diagonal we have sigma i's and 0 everywhere else. U is a storage unit for singular left singular vectors, UIs, and V is a storage unit for the right singular vectors, V i's. Just like that. Both U and V are orthogonal matrices, and sigma is diagonal, just like before. Good. So that's singular value decomposition in the matrix form. Perfect. In the geometric form, what does a matrix do? That's a very general question. Now we have a completely arbitrary matrix. How can it act as a transformation? What does it do? So it takes the vectors Vi in the original space, and let's see, what does it do? It takes vectors Vi in the original space, then it transforms it in the following way. It not just stretches it, but it first rotates it. So it maps Vi's first to Ui's, so right to left singular vectors, and that's a rotation. So it first rotates it and then it stretches these directions, lambda, and becomes lambda I Ui. So we first rotate and then stretch or compress. UI lambda I times sigma I times. Should be sigma I here, singular vector, singular value. Okay, so the singular value decomposition is actually a non-trivial idea that any linear transformation in space is just a combination of the two things, rotation and stretch. Good. Good. The optimization form should be obvious now. Like if you, it's kind of obvious from this that this direction, that VI direction, is a direction in which the linear transformation stretches the most. So it takes that and then it makes it the largest here. And we can express it in the following way. We just maximize the norm of AX over all unit vectors X. And the largest action is going along the direction of V1, the first singular vector corresponding to the largest singular vector. So V1 is argmax. And similarly, sigma 2 is, now what do? Now we take the first direction, factor it out, so we forget that. V1, so we project everything orthogonal to V1, and in that residual we optimize again, and we get V2. And so on and so forth. Then at the very, very end, we get the last one, the last direction that stretches the least. So in the very end, we have the minimum of AX over all unit vectors. And the minimum is attained at the last singular vector. Maximize and minimize and do all these intermediate things just by looking at the spectral problem. Okay, any questions? Okay. Couple interesting remarks here. First, if we even go back, I forgot to say that, sorry, for the optimization form of symmetric matrices. You see, this is a X transpose AX is a quadratic function. Right? This is something like the sum, double sum, Aij, Xi, Xj, quadratic function. And usually quadratic functions are not easy to optimize. Like I give you a set, I don't know, a cube, for example, and you optimize this quadratic function. And that was what we dealt with in Grothendieck's identity. The whole problem was that it's not easy to optimize quadratic functions, even on a cube, even on a continuous cube. But on the sphere, so on the sphere, X is unit, so this means that we're optimizing only on the sphere. It is actually easy to optimize quadratic functions. On the ellipsoid, the same way. It's just you can transform the ellipsoid to sphere. So sometimes, by a miracle, quadratic functions are easy to optimize. This is one of these miracles. You just how do you optimize? Well, you just compute the diagonalized symmetrics. You just compute the eigenvalues, eigenvector, and that's it. The first one will be the optimum. So such problems are called spectral problems. This is so optimizing a quadratic function on a sphere, and by extension on an ellipsoid, is, well, not say it's easy, but it's tractable. It's computable in very short time. It's tractable by computing lambda 1 and u1. The spectrum. So this is called a spectral problem. So whenever possible, people would like to relax their problems, the hard optimization problems, to spectral problems. That'll be the easiest approach. If it works, then it's great. Because spectral problems are done by just computing the eigenvectors. And similarly here, still a spectral problem to optimize the length of a vector, let's say on an ellipsoid, on a sphere. That's an easy problem. Spectrum. Good. Okay, cool. Let's look now at these two extremes. So sigma 1 measures the biggest distortion, like the biggest stretch that this linear transformation makes, and sigma 1, and sigma n measures the smallest stretch, like the largest contraction. Everything happens in between, right? So if you think of how A acts, it stretches and contracts different directions, and these are the two extreme ones. So in particular, so let's make this remark about extreme values. The meaning of the extreme singular values is this: sigma 1, I'm just rewriting it here, but I would like to normalize differently. I would like to not normalize x at all, but just divide by the norm of x. Is it clear that this is the same? Yeah, just divide. So if x is any vector, you apply this for x divided by the norm of x by the unit vector, and you get it. So and sigma n is the minimum over all x except 0, like this. So these two, they measure distortion, the maximum distortion of geometry of the space under the transformation A, just in the Johnson-Linderstrauss lemma. For example, AX minus AY. If you take 2 points and A acts on them, so you take two patients, let's say, and we have this transformation that takes them somewhere else, and we ask how far they are now. How is their distance changed? All right. So this is A times x minus y by linearity, and then we apply this singular value, so it's less than sigma 1 times x minus y. And here I'm just applying this interpretation of sigma 1, but for the difference, for x minus y. And it's greater than sigma n, okay, times x minus y. And this happens for any x and y in space. So for example, if you would like an isometry, the map that completely does not change the distances, like orthogonal metrics, then sigma 1 and sigma n will be the same. And this will be all identity. And therefore, all intermediate singular values will also be the same. That's an ideal case. And generally they're different, and this is their meaning. Okay, good. Okay. Any questions about this? Okay, so we covered this kind of pressure that many of you already know. It's about eigenvalues and eigenvectors, and singular values, singular vectors. Perfect. So now a little bit something new. We're still doing this refresher in the algebra, but maybe you haven't seen that before. Matrix norms. Pretty soon we will we'll be approximating matrices. We would like to approximate, let's say, I don't know, a covariance matrix of a distribution with some sample covariance obtained from the sample. So we would like to know how matrices are far apart from each other, how are close to each other. This can only be measured by some metric, right? So if I want to say that A is close to B, I have to have some metric, some kind of some idea of how do you measure distances or lengths of matrices. And there are many very natural ways to measure the length in the metric space. The two most popular and easy ones is the Frobenius and operator norm. So first, Frobenius norm. Frobenius, functional analysts call it Hilbert-Schmidt norm. Super easy. You just think of a matrix as a long vector, and you do the usual Euclidean norm on it. You just pretend the matrix is actually, you concatenate the rows, and you pretend the matrix is a very, very long vector, and you think, just take Euclidean norm. So the square of that norm is what? Euclidean norm. So you just sum all entries squared. That's it. So this is just Euclidean norm on this space M times N. Okay. Have you heard Frobenius norm? Did you hear about this? Okay.
Yes.
Yeah, good, good. Okay. So that's Frobenius. It's a Euclidean norm, so it means that it's a Hilbert space. It means it's not only a norm, but it comes from the inner product. There is a canonical inner product on Euclidean space, sum of xi, yj. So the inner product. Let's look at it. What it looks like. Inner product between two matrices. Now we can define inner product of two matrices. That's cool. So how do we define inner product? It's we take the entry, we multiply entry by entry, and then we sum over all entries. That's a dot product, just the usual definition. And we can rewrite it in the matrix notation. It's okay. So okay, be with me. So don't write this down yet. I'm trying to reconstruct this. So if this was, instead of ij, if I put ji here, if this by miracle was ji, then we're multiplying the matrix A by matrix B. That's how we multiply. Right? And then we take the trace because that corresponds to taking the sum over i's. So by the first sum over j's will correspond to the product AB. The second sum over i's will correspond to taking the trace of AB. So this would be the trace of AB if I swapped j and I. You agree? Is it hard to see? Multiply AB, you get that. So sum of I, that's a trace, and then sum of j, aij, bji. So this is how you multiply matrices. You get the i's entry this way, and then you take these I entries, sum them up, and get that. Okay, but we don't have that. We have not ji, we have ij. So the only change, but that's okay. The only change I have to make to this argument is that we take the trace of A transpose B, of A B transpose, it doesn't matter. So check this a little bit more carefully than I did here. And the inner product should define the norm, and that's a Frobenius norm. We know that already, so everything is good there. So this is true. Okay, so Frobenius norm will be, it's the simplest norm on matrices. It's explicitly written in terms of matrix entries, perfect. You compute it in one step, no problem there. It's a very simple norm to control, and it's very useful in data science to control the errors, the distances between matrices. Let's note some cool properties of this Frobenius norm. First of all, it's orthogonally invariant. So orthogonal invariance, which means that it doesn't change if you rotate the matrix. So for any orthogonal matrices, U and V, UA has the same norm as A, and AV has the same norm as A. So you can multiply on the left, on the right, everything is good. Okay, let's prove it. It's super easy. But actually, it's not that easy if you just work out the definition, because you'll have a huge sum. But let's do this proof. So let's say UA, Frobenius norm. Okay, cool exercise. So Frobenius norm squared, that's the inner product between AU and AU in this big matrix space, which is the same as a trace of, just by definition, it's a trace AU transpose. UA, sorry, I missed that. It's UA. UA. So it's a trace of UA transpose. UA. Cool. How do you take the transposition? You'd swap the order. So A transpose, U transpose, UA. Aha, now a miracle happens. So what does U transpose U?
Identity matrix.
Identity, that's kind of a definition actually of the identity matrix. Sorry, definition of the orthogonal matrix. U is orthogonal, and therefore U transpose equals U inverse. So that's identity. That's because U is orthogonal. Perfect. Thank you. And we have trace of A transpose A. Then we work it back, like reverse engineer, trace it. That trace is the inner product of AA, and that is the inner product. And that is the Frobenius norm squared. That's it. Yeah, cool. So it's rotation invariant. Very good. Any questions about this, about the proof? Okay, now the coolest property of the Frobenius norm is that it can be both explicitly written in terms of matrix entries and in terms of eigenvalues, actually singular values. So it is both, it works in both spaces very nicely on the level of entries and on the level of the spectrum. And so here's how. So here's proposition, extremely important, is that the Frobenius norm is actually also the Euclidean norm of the singular values, which is sum of the singular values squared. It is cool. Like you can sum the entries squared, and you can sum the singular values squared, and it's the same number. Okay. So proof. The idea is that A is diagonalizable, really. So A is what? A by singular value decomposition, A is U transpose sigma V. That's a singular value decomposition. But the Frobenius norm doesn't care about U and V. It should be transpose here. The Frobenius norm by the orthogonal invariance doesn't care just like we proved, we can get rid of u and v's. It's the same thing. By orthogonal invariance, which is this. Yeah, so whatever multiplied by orthogonal transformations, they're gone. And we have the diagonal matrix. And recall what diagonal matrix is. The diagonal matrix has just the singular values on the diagonal, and the rest is 0. And so what's the Frobenius norm of that? Well, that's easy. You just sum all entries and the squared, and that's sigma I squared. That's it. Done. Good. Good. Okay. Any questions about this? Okay, so Frobenius norm is very, very simple, very, very useful. We'll see how. It's already kind of hints how it is useful, that it has explicit representation in terms of entries and has explicit representation in terms of spectrum. So whatever you know about the metrics, you can compute Frobenius norm just easily. Unfortunately, Frobenius norm is too strong. If you measure errors with respect to Frobenius norm, and you hope that your algorithm, let's say, is accurate, gives good accuracy in the Frobenius norm, good luck. It's usually a miracle if the algorithm works like this. We can take some weaker norms. Let's say we can, instead of taking the sum of the square of all entries, we can take the maximum entry, for example, AJ. That's another norm, like an L infinity norm on the matrix. But unfortunately, it doesn't have the spectral representation. So nice results like this are not available for it. And so people don't really like that one. There is a norm, maybe, I don't know. No, there are others, but I think there's about one other norm that I know that has both representations, again, that both on the level of entries and on the level of spectrum. And it is this. It actually is a norm. This one. The first singular value. The first singular value of this matrix is a norm. It's called the operator norm. If you've studied a little bit of function analysis, then you may recognize it as an operator norm between two spaces. If you haven't studied that, then it's actually not so difficult to see that it is a norm, that it satisfies triangle inequality. If you fix x, for example, then definitely it satisfies triangle inequality. If you then take the maximum, it still satisfies. So that will happen next class. We will define this as an operator norm and find that also already found it that it has a spectral representation. So it's just a first singular value. Unfortunately, it doesn't have a nice expression in terms of entries. There is no closed form expression. Like I give you this matrix, let's say the matrix entries is 7, 3, 2, 1. What's the operator norm? How do you do that? You have to diagonalize the matrix first to know. So that's the only downside. But it is a nice norm that's definitely smaller than the Frobenius norm. Because for Frobenius norm, you'd have to sum the square of all entries. And sorry, the Frobenius norm is you have to sum all the singular values here squared. And the operator norm is just you take the maximum, the largest one, which is smaller, obviously. So it's not as restricted. So that will what will happen next, and then we will go into covariance estimation and PCA principal component analysis with finite samples, guarantees for that, and further on. But I should stop talking now. But any questions, anything, any observations, philosophical or otherwise?
So it also seems that between the Frobenius norm and this operator norm, you can also take the first k singular values. Are there kind of something like that?
Yeah.
If that makes sense.
It totally makes sense, but I forgot which one is which. So I don't think it is as easy as, for example, sigma 1 will be the norm. I'm pretty sure about this. Sigma n is not a norm. I'm also pretty sure about this. In fact, by swapping this, sigma n is actually 1 divided by the norm of the inverse of the matrix. It's just the way it goes. So it is not a norm in itself. What happened? And so I believe that after the first one, it's not a norm, but you can cook up norms using this. And I don't remember how to do this. It's like, I have to check. Some norms are available, but it's not just taking this, like the 13th singular value. That alone will not do, but there is some combinations that will become a norm, but I can't remember them. And they are important too, yes. Yeah. For instance, you can take, instead of taking this like this, this is basically the L2 norm of this singular values, but you can also do something like this, a to the p, and call it, you take 1 over p just to normalize things, and you call it CP. So this is actually a norm. It's not easy it's not immediately clear that it is a norm, but it is actually a norm. That's called Schatten norm. For any p between 1 and infinity, including infinity, for which it would be the operator norm, the sub. Yeah. Which actually, well, let's speak, I'll tell you a story. So, for example, the C1 norm is the sum of sigma i's. It's like an L1. I don't take absolute values because they're automatically non-negative, but just for visual purposes. So this is like the L1 norm on the on the singular values, right? Okay, how is this useful? Now remember, if there was anything like C0 norm, which is the number of non-zero sigma i's, that would be the rank of A, the number of non-zero eigenvalues. So that will be the rank. And rank is not a norm. It's very unstable. But sometimes you want to minimize rank or minimize rank usually, right? So you actually want matrices to have small rank in approximation. And what you do is you choose the first P for which it is a norm, and that's 1. So C1 is a proxy for a rank. So that's how you convexify or relax a rank to something convex. If the algorithm optimization algorithm requires to use the rank and it is impossible because it is non-convex, then you automatically replace it with C1 norm, the Schatten 1 norm, and that works. It's a convex norm. Any other observations, questions? Good. Okay, guys, we'll then see you on, let's see, I'll stay here if you need anything about the homework or anything else, but I will stop recording now and we'll see you on Wednesday then.